Welcome, welcome at this Getting Technical event. Today's subject, and I have been looking forward to this since a while now, is advances in stainless steel machinability. Stainless steel was once a very big challenge for machining people, and today it's evolved into a material which is, from a construction perspective, quite a lot used in the industry, but yet there is quite some development going on in insights in exactly how it goes when we do machining. And I want to focus on that. You have in the meantime what I would say is very much known knowledge about how to machine stainless steels. On the other hand, we still learn a lot when we do machining, and now and then that leads to different approaches in how to do. And I use an example here when I was the first time confronted with stainless steel. That was, and I'll never forget it, in 1986. We had a project, and the project was to focus on stainless steels, because in those days it was rather seldom we saw it in a workshop. But when we met it, it was a big challenge. And the big thing was there were not really tools available for it, and we didn't really have knowledge about the material. So we were confronted with uncertainties. And the project I'm talking about was about understanding this material better. And knowing what it means when we do machining, and with other words, knowing what we can expect from a cutting tool in such a material, and how we would select cutting conditions and so on. And based on research then, in those days, we thought a major thing in stainless steel is the corrosion resistance. Because corrosion resistance leads to the formation of a very thin layer on the surface of a workpiece, a chromium oxide layer. And that gives the stainless steel that typical shiny view and resistance against oxidation and corrosion and stuff. And we thought that is the source of all our problems, because we thought we found something. Now, after all these years, we do realize that corrosion resistance is not really the big thing when we do stainless steel machining. So new insights. What is new in this domain? My name is Patrick de Vos. I learned the trade with Seco. I was 40 years in Seco. Since a while now I'm retired, but I'm so passionate about machining and knowing about machining and sharing knowledge and teaching people about the beauty of this trade, that I continued working. I started my own company, and I focus on sharing knowledge, distributing knowledge in the machining sector. And if I look to machining over the years, there is a model I have in my head I developed over time. Machining is a process, when it's steel machining at least, or let me say metal machining, where I deform material, I deform it so much it shears off, and the shorn off material is evacuated under the form of a ship. Now, this process, deformation, shearing off, involves quite a lot of things that are ongoing. You have mechanical effects and thermal effects, tribological effects are taking place, and all of that is influencing how the process is going. If I have a kind of a balanced process, because machining is a situation where loads are acting on a cutting tool, and a cutting tool has a load bearing capacity, and those two needs to be in balance. And that balance equation, kind of, we could call it, that machinability equation, is influenced by a lot of variables, which I line up here in the left part of the picture. These are variables, on the one hand, from the cutting tool, giving it load bearing capacity. From the other side, the environment in which the process takes place, that is going to put certain loads on the cutting tool. These are the variables we need to bring together and solve that machinability equation, so that the result of the process is in line with our expectations. Now, solving that equation demands quite a lot of how to say, knowledge, skills a machinist has to possess. He has to understand the physics of the process. He has to be aware of, I would say, economical considerations, costs and productivity and stuff like that. He needs to make sure he's using at all time the best technology available, not only cutting tool technology, but also, for instance, digital possibilities we have today to control this process. We have to embrace them, the attitude of people. So it's quite a lot of things we need to take into consideration. And we need, of course, to measure. To measure is to know. We need metrics. And metrics in machining we find in cutting tool evaluation. Used cutting tools tell us so much. We learn from workpiece evaluation. The quality, is it in line with expectations? We learn it from asking the operators. Those people are standing all the time very close to the process, and they have their observations based on their experience, what they expect and didn't expect, and stuff like that. And of course, ask customers, ask the people for whom you are producing the parts, if the part you deliver is in line with expectations, both price expectations, delivery expectations, quality expectations, all of those things. Because that's the result. The result of a machining process is more than just a correctly finished workpiece. It's a correctly finished workpiece in a certain economical situation. If you want to read about these things, there's quite a lot of literature available from Seco on these subjects, which you can ask for at all time. But very important to realize is that I'm not alone here. I'm together with my two I can say friends in the meantime, Alasia and Margarita. They are helping to make this happen from a digital technical perspective. I have the fun part. I can do the presentation. And what I want to talk about is, in the first part, stainless steel. So what is it, and what are the latest developments, and what are the challenges, what are the properties when we are having to machine these materials. The second part is more a lineup of advice. If you have to machine stainless steels, think on this, do this, don't do that type of stuff. A collection. Kind of, one could say the first part of the presentation is more the academic side, while the second part of the presentation is more the practical part, the experience from real life I brought together, kind of. Now, stainless steels, first the definition. A stainless steel is a steel alloy. Main alloying element is chromium, and when in a steel chromium alloy, there is at least 10.5%, and there are different opinions and definitions depending on certain standards and norms here, but at least 10.5% chromium should be present in the structure. Then we talk about a material with a certain resistance against corrosion, staining, rusting, and that is what we call a stainless steel then. Of course, we add all kinds of other alloying elements to this structure to give the material, next to corrosion resistance, one could say, also other wanted properties more in the mechanical domain, like like hardness and that type of stuff. Stainless steel, once being rather unique as a material 30, 40 years ago, today as a construction material is widely used in the industry. You find it in all kinds of applications. And if you look to stainless steel, because stainless steel is a family name, a very big difference between different type of stainless steels is the structure of the material. And that's why we group stainless steels in I would say 5 different groups. You have austenitic stainless steels, ferritic stainless steels, martensitic stainless steels, duplex stainless steels, and the so-called pH steels, precipitation hardening steels. Each of these subfamilies has its own specific properties, and if we have to machine the material, we will see differences. Now, so you have ferritic, martensitic, austenitic, and duplex. I keep pH steels a bit on the side for the moment. And all of these materials, or material groups, I would say, they kind of, are connected to each other because one structure goes into another structure, and we should avoid here to become too metallurgical because otherwise we are going to get lost in time. It's all depending on which alloying elements you are adding or extracting from a structure, and by doing so you create different type of material properties. Now, most of the time, we use kind of the ASI system here. People talk about the stainless steel from the 400 group or the 200 or the 300 group that relates to the structure. Very typical, I would say, kind of, I think the basis of stainless steels, if I look around me today, if I look around in workshops, the most seen structure, if you want, is austenitic stainless steel. Austenitic stainless steel, it's the 300 series when you talk about designations. It's stainless steel in which there is chromium as an alloying element and nickel. Nickel is added to chromium stainless steel to strengthen the structure. And that combination, steel, which is iron and carbon, chromium and nickel, that's the chromium nickel steel, the 300 series, austenitic stainless steel. So there are three classic types, one could say. You have martensitic, ferritic, and austenitic stainless steels. It refers to the structure. An interesting practical thing to remember, if you are confronted with a stainless steel and you say, I don't know, what is it really? A big difference between austenitic and the others is that austenitic is non-magnetic. So you can take a magnet. If the material you have to machine is non-magnetic, most probably you have austenitic stainless steel. Next to these three basic types, you have the duplex stainless steels. Duplex stainless steels, as the name says, it's a combination of structures. It's a development that a couple of years ago went very fast. All kinds of duplex stainless steels were developed. And for us machining people, duplex stainless steels give a kind of a challenge in a way that it's not always obvious on what to focus now. Which structure is it the austenite or is it the ferrite in the structure we have to focus on? That's a bit of a selection challenge we have when we have to machine duplex stainless steels. You have the pH stainless steels, precipitation hardening stainless steels. It's a Swedish development. It's a Swedish metal or iron industry that came first with this type of materials. pH stands for precipitation hardening. It's a material which is developed to react rather fast to thermal treatments. I'm going to say something which is not correct, but anyway, it's kind of a self-hardening material. If you add heat to it, it starts becoming stronger, harder. Now, that sounds very good, but for us machining people, that's a big challenge, because if you add heat to it, what do we do in machining? To a big amount, we add heat to the workpiece material. So we could end up in unwanted situations with this type of materials. There is a sixth group, also a Swedish development. It's like the Swedish industry thought, we have to compensate now for this pH stainless steel. And that is a group which is the easy machinable stainless steels. It has basically nothing to do with the properties of the material. It's just stainless steels to a certain extent where calcium mainly is added. And that calcium creates something in the structure that makes the stainless steel easier to machine. We are confronted with less challenges. Mainly, it gives us more freedom to work with different cutting speeds. Traditional stainless steel, the cutting speeds are rather low. I don't say low, I say rather low. Everything is relative. And people feel that as a limitation when they talk about productivity. Taking that limitation away, that was the aim with the calcium-treated stainless steels, where suddenly you had a lot more opportunities to work with bigger cutting speeds. Of course, that comes to a cost. The cost is, in general, if you take a stainless steel or a calcium-treated stainless steel, the calcium-treated stainless steel, from a purchasing perspective, a material purchasing perspective, is more expensive. On the other hand, it could be a well-done investment if you look afterwards to the productivity you can gain in your machining applications. Stainless steels are more and more the normal materials. What we see is that very often the applications, the parts are rather complex. Technology is sometimes a challenge. Quality is always looming around the corner, because these are typical workpieces where quality demands are higher. When quality demands are higher, you have higher efforts for inspecting workpieces, finished workpieces. So that is what the machinist is confronted with in general in this type of applications or in this type of workpiece materials. Now, machinability, workpiece material properties, machinability. I guess you are all familiar with the so-called ISO system. ISO, where we group materials in 6 different groups, and then from there on, we say, okay, define where your material you have to machine is belonging to, and for a certain material group you receive some advice then concerning tool selection, cutting material, geometry, cutting conditions, and so on. Stainless steels is one of these groups. It's the so-called M group. That's why a lot of people refer to stainless steels as the ISO M materials. It's one of those sayings, in the machining world. Now, if you look to the traditional ISO system, they mainly focus on mechanical properties to classify materials. And for a long time, as I said, when we looked to stainless steels, we saw the mechanical properties, we saw the results from machining, we saw wear patterns, we saw tool life, and it was a bit of, we did not really understand. Because tool life was lower than expected. Tool wear was more severe than what we expected based on purely mechanical properties. And that's why 10, 15 years ago, there was a big project, again in Sweden, where the steel industry and tooling people worked together and tried to figure out, is it enough to base machinability ratings on mechanical properties only. And the result of that big project, which was led by Professor Stahl from Lund University, was that next to the typical mechanical stuff like hardness and abrasiveness, the ductility, there are other things that influence how a material will or a material property will influence a machining process. And the 2 main ones are strain hardening effects. Some materials become, when you deform them, harder, and machining is a deformation process. And thermal conductivity. During machining, heat is generated, and to which extent is it possible to evacuate the heat away out of the cutting zone, yes or no? That means, and that's what I try to illustrate with the videos you just saw, that a machining process, you have a mechanical side to it. In this diagram you see with the 5 axes, which is a visualization from the model developed. The left side is the mechanical side, ductility, abrasiveness, hardness, typical mechanical properties. The right side is more the thermodynamic side of it, one could say. Strain hardening effects, low thermal conductivity, ductility, adhesiveness, the vertical axis is a bit on both sides. So if we want to understand how a material behaves during machining, there are 5 properties we need to take into consideration. And the interesting thing on this model is that the old saying that flank and crater wear is the only acceptable wear during a machining process, which is very correct if you machine steel, but which does not really work if you have to machine another material, that we can improve that, and that we can say it's one of these 5 properties, and to which extent the property is there in the material, is present in the material, that if you machine the material, you will see a certain typical wear pattern on a cutting edge. And that means that if you are confronted with a material and you want to figure out how should I do machining and which tool and which carbide grade or cutting material in general and which geometry and feeds and speeds and things, and you do certain selections and you observe the process and you look at used cutting edges, you can much more precise now saying, okay, what I see is what I expected or not. And if not, I have to redo the exercise. I think that's perhaps the most beautiful thing on this system. It makes wear control, deterioration control, much more easy or predictable. Now, if I look to stainless steels, they have a certain structure, they have alloying elements, there are mechanical properties, and so on and so forth. It's the ISO M group. But if I look, and if I try to put it in the 5-dimensional thing, if I look to ferritic stainless steels here to the left, or martensitic stainless steels to the right, what you see is, if you compare it with traditional steel, the blue thing, for the 5 properties, imagine I take steel as a known material. I know the tools, I know the cutting conditions to give good results. And if I compare the 5 properties then, well, here you see ferritic stainless steels. It's nearly like steel. That's why there are some discussions that, ferritic stainless steel should not be put in the ISO M group, but perhaps rather in the ISO P group. But I don't want to interfere with these. Ferritic stainless steel, whatever you know from steel machining, you can nearly copy it one-to-one. If you look to martensitic stainless steels, here you have, in general, I would say, a material which is a bit harder, a bit more abrasive than traditional steels. But you see that the thermal conductivity here starts to be lower, very lower, compared to steel. That means that we have to be careful with the heat which is generated, because if more heat is generated, it's not that easy to evacuate it away from the cutting zone as it is in traditional steel, meaning that the cutting temperature will go up higher than what we are used to. And that has consequences. That has consequences for tool selection. That has consequences for cutting condition selection. If we look to austenitic stainless steel, and I put this one in the middle because it's the one we find mostly in the industry, in the workshops today. Here we see, with the exception of hardness, that austenitic stainless steel, compared to traditional steel, everything is more present. It shows higher abrasiveness, higher ductility, higher adhesiveness, higher strain hardening, and seriously lower thermal conductivity compared to steel. So machining austenitic stainless steel demands for, and that was the challenge back with the project we had a long time ago, it demands for tools specifically designed for a different type of environment. It demands for cutting conditions which are selected in line with what the cutting edges will be submitted to. To make the picture complete, pH stainless steels, precipitation hardening stainless steels, you have to worry mainly there about abrasiveness. Ductility will be a lower of a thing. Ship control will be easier than normal, but abrasiveness is the thing to worry about in pH stainless steels. Duplex stainless steels, as I said, if you compare them with steel ruffling, everything is more severe there. But the thing with duplex stainless steels is that we don't know exactly, workpiece by workpiece, which one will be the prevailing one during the actual operation. For sure is that low thermal conductivity is also a major thing there. So, and I use the example here of austenitic stainless steel. If you are confronted with an austenitic stainless steel, How to select tools? Yeah, focus on the red parts here. That are the demands we have for cutting tools if you want to take into consideration the typical properties of stainless steel. The red ones are the important ones, the critical ones. The orange is be aware of, and black means there is no difference with steel machining. The same with cutting conditions. Focus on the red parts, because compared to traditional classic experience in steel machining, we will see differences there. Keep your eyes on used tools. Used tools will tell you how well you made your selections. Something I would like to add here is that if you do thinking in that type of thing, what would be, because we always talk about what would be a good tool, what would be a good machine, what would be a good geometry, and so on. And what would be a good operator? What is a good machinist? And also there we can say, and it's in that line that this type of presentations fit, a good machinist is somebody with knowledge, huh? And insight, and knows what's going on. If you stand next to a machine where you see stainless steel being machined, you see things. And based on what you see, it tells you a story. Anyway, machining of stainless steels, tool wear will be faster than what you are used of. That means that in general, machining costs will be higher than the ones we normally have in traditional steel machining. Tool changes will be more frequent due to that you have shorter tool lives in general. And if you have more frequent tool changes, that means that your machines are going to stand still, relatively seen more than in steel machining, and that's going to lower your productivity. On the other hand, if you look to workpiece quality, you are going to be confronted with some things that will demand for post-machining processes, deburring and stuff, and that will also lower your productivity. And I draw your attention to this, and later on I want to line up some things. Production economy, having an eye for costs and times and so on, when you do stainless steel machining, I would say should be on a higher level, and it's dangerous to make statements like that, but I hope you understand what I mean. It's a more important thing than traditional steel machining. Not saying that in steel machining it's not important. Don't put words in my mouth that I didn't say. Stainless steel machining, insights and practical experience, bringing it together, that's what we want to do. We are confronted with a material with a higher toughness. Higher toughness means higher cutting forces. It means increased tool wear, faster tool wear. That are the things we have to worry about. Strain hardening tendency. I have been talking about strain hardening tendency, which is always present to some extent in austenitic stainless steels, for instance, very much. It leads to very specific tool wear patterns. It leads to surface roughness considerations that are important. Tool life could be limited due to that. Lower thermal conductivity, perhaps the most important thing. Lower thermal conductivity means that heat generated during the process is not evacuated, stays in the cutting zone, and we will have to balance that by tool selection, cutting condition selection, machining strategy selection. Higher hardnesses for some. Think on martensitic stainless steel, austenitic stainless steel, it's less a thing. What I'm trying to give you here is an overview of properties you should be aware of, you should be informed of if you have to machine stainless steel, so you can make sure you do your selection process in line with this. Adhesion tendency, the formation of build-up edges. Austenitic stainless steel has a higher adhesion tendency and a tendency to gall. Now, here I would like to make a difference between the two, because adhesion is a part of the workpiece material connects to the cutting tool. It's a rather soft connection, so it's easily broken off from the cutting tool, and it could lead to shipping of a cutting edge. That traditional build-up edge stuff. Tendency to gall, with that I mean, is that in some cases the material that connects to the cutting edge connects so much that it breaks away a little bit or a part of the machine surface on the workpiece. And it seems the same phenomena, but it will give you other types of issues, because then it's going to deteriorate the quality of the machine surface of the finished workpiece, and we have to be aware of that. Corrosion resistance, as I said, and here just for sentimental reasons, I bring that corrosion or anti-corrosion layer again on the table. Where people say, okay, if you know the PRE factor, and the PRE is a factor which we use for defining kind of the quality of a stainless steel, the higher the PRE, the higher the corrosion resistance is, one could say. But if you have high PRE, it means that you have a strongly formed anti-corrosion layer, chromium oxide layer, and if we have to machine through that, it has consequences. 40 years ago, we thought that was it. Today, we know better. We know that this plays a role, but much more is the formation of a strain-hardened layer on a machine surface that influences how the process goes. Impact of heat is very important. Here you see, and it's a classic picture. I think most of you know this picture. It says that depending on the cutting temperature, certain phenomena leading to certain types of wear become dominant compared to others. Traditional wear patterns, abrasion, diffusion, chemical wear, one could say the higher the temperature, the more severe they take place. Adhesive wear and galling wear, the picture is different. That will happen at certain critical temperatures. And if your temperature is lower or higher, then it will disappear again. That means that in stainless steels, we talk about a low performance domain and a high performance domain. Low means that you keep your temperature lower than a certain critical value to make sure that adhesive wear does not take too much out of the cutting. High productivity means that you are able to take your cutting speed high enough to pass the dangerous zone, and again have temperatures which are not favorable for build-up edges to be formed. It's a selection you make, it's depending on the equipment you have, it's depending on the workpiece you have. Can you go for higher cutting speeds, meaning productivity? Yes, good, do it. Can't you, go low. It's something to bear in mind. General guidelines: if you machine stainless steels, stable tooling, sharp geometries, large depths of cut and feed. It's all based on experience. Change cutting edges regularly. Remember that you will use more cutting edges. Tool life will be shorter. Think on it that stainless steels, you have hard surface layers, chromium oxide, strain-hardened layers. Think on heat development. It's limited, because you could end up in critical temperature things. Chip thickness is very important. The thickness of the chip, because the thicker the chip, the more it has the possibility, the capacity to evacuate heat out of the cutting zone. Thin chips don't have that. That would make the problem with too high temperatures in the cutting zone even worse. Use big tools, have a big mass to evacuate heat. If you reduce your cutting depths, then you should increase your cutting speeds. Remember, it's not about low temperatures, it's not about high temperatures, it's about avoiding some critical temperatures. Specifically in milling, like in general, turning, drilling, whatever, strong tools, sharp geometries, large point radiuses, especially for end mills, I'm thinking, big depths of cuts and feeds, change the milling cutters or the cutting edges in due time, cut under the hard layers, do down milling if possible, limit the heat development, use cooling, use it correctly. Average chip thickness. Chip thickness is in general important. The so-called average chip thickness in milling is even more important. Avoid feeds 0, because then you have strain hardening extremely taking place. maximum volumes, carbide volumes to evacuate the heat. And also here, small depths of cut means high cutting speeds. The so-called speed factor in milling applications is a very important thing when you machine stainless steels. Conclusion, you will need more cutting edges than at first sight, perhaps what you thought when you compare to steel machining. Be careful with things making life even more difficult, interrupted cuts, casting scales, casted stainless steels, and be careful with false economy, because after a roughing operation, there comes a finishing operation. What you see here, I try to visualize a turning application followed by a threading application. If you use in the turning application your cutting edges too long to save money, you could create strain hardening layers on the surface where later on a threading tool, which we use with small feeds and depths of cut, it's impossible to cut through. And then you are going to save on turning inserts, and you are going to spend a hell of a lot of money on threading inserts, which are more expensive. I mean, keep your economy right. Make sure you do the correct steps here. Fully understand stainless steel. Tip 1. And how it relates to machinability. Strategic thinking on tool selection. Machining strategies and cutting conditions. And more important is geometry than cutting material. Again, I don't say cutting material is not important. Cooling is an important thing here. Wear monitoring. Your tools will wear out faster, so especially when it's new, make sure you follow up. Clamping. Stainless steel is a typical material where we will have micro vibrations. Clamping and fixturing of workpieces and tools is important. Make sure the work environment is as neat as possible. That's a bit beyond the actual cutting. Make sure people have the needed education and knowledge to understand the material they are machining, so they can react in the appropriate way when they are facing something, and make sure to analyze regularly machining, and what you learn from the analysis to document it, to keep track of it. It's very valuable information for you. Things you should always do if you machine stainless steels. The correct tool. As I said, the big problem in the past was we didn't have correct tools for stainless steel, led to a lot of problems. Today we have the correct tools, make sure you use them. Sharp cutting edges is a major thing. Stable machining, you will be confronted with micro vibrations, so be aware of that. Cutting fluids, cutting systems are important here. And cutting data must be in line with the material you have to machine. It all seems normal, but trust me, I see so often when I'm in a workshop that these basic stuff is not always respected. Cutting temperatures is the thing you have to worry about. Make sure your equipment, being the machine tools, but also your cutting tools, are in the best possible condition. Ship removal is important, because you will have more difficult to evacuate ships, so it deserves some more attention. Cutting speed domains, remember it's not as high as possible or as low as possible. There is somewhere a domain you have to be careful with, depending on temperatures. And again, keep track of your observations and make sure it's available for everybody who needs it. Too much worn tools should be avoided. Keep your eyes on the tool and make sure you can read the signals correctly. High cutting speeds, okay, but think on how cutting speed leads to more heat generation, and heat generation potentially will increase your temperatures, and that could be an issue. Cutting conditions should be different depending on the type of stainless steel. There is not one cutting condition for stainless steel, all of them. It's a lot of different type of materials. Cooling, I already mentioned how important it is. Ship clearance, make sure the ships go away from the cutting zone, especially in milling applications, I would say it's an important thing. Cooling should be adapted to the application. Preventative maintenance should be at all time. It's a bit in line with what you should do. So what you should not do is here. Rigidity, lack of rigidity is a dangerous thing. And again, untrained, uninformed operators, engineers is not a good thing. A few words on cooling. Cooling systems I want to focus on. Flood cooling can work in stainless steels in most applications. Mist or aerosol cooling, the so-called MQL cooling, be careful. In certain circumstances it can work. High pressure cooling, can work, especially there where ship evacuation is a major thing. But coming to the two interesting ones, perhaps for stainless steel, or more interesting than the traditional ones, is the so-called HPDC type of cooling, high pressurized directed cooling. If you compare that with other cooling systems, this really gives very noticeable improved situations. And cryogenic cooling, perhaps that's a little bit too much still in academical environment, but it gives promising results. General purpose, machining of stainless steel, flood cooling, rich emulsion flood cooling is most of the time okay. More difficult materials go for high pressure cooling. High pressure HPDC or cryogenic, if you go for the really, or if you chase really high productivity, are the types of cooling you should be aware of. Tool deterioration, one of the metrics we have to evaluate if things go well. You have the traditional things we say about tool wear. If we talk about, and I use the example here of austenitic stainless steel, for each of the different families, you can draw up a picture like this, but austenitic being the most common stainless steel still today. Depending on which properties exactly you are confronted with, and again here, red means that is going to be major there. One can evaluate used inserts in line of what is the primary wear, because that's what I try to show with the two photos here. If you machine stainless steel, most of the time you will see combined wear patterns on a cutting edge. And then the question is, which one is the primary one, the most important one? The one leading to a certain tool life. What is preferred? What is expected in line with this concept? What is common? And if preferred and common, I mean what you see mostly, is not in line, how to bring it in line. That is what you are confronted with. Duplex stainless steel, just wanted to give you the view. With duplex stainless steel, depending on the actual material, you will be kind of confronted with all kinds of different combinations of these 5 properties. And that means that wear analysis is a difficult thing here. It demands for well-educated people, well-trained people to be able to handle this. What is the primary wear, and decisions will need to be taken. What is preferred and what is common? If not in line, how to balance. Now, it's a more difficult material. No, I should say it's more expensive to machine stainless steel than it is to machine traditional steel. That means that production economics is on a higher level important. And I would say production economics should even be somewhere in the head of the operators in case of stainless steels. And some basic things is cost benefits comparisons. I can buy a specific tool for stainless steel, but it's more expensive. So okay. But by using that, what are the benefits? So make sure you, at all time, if you compare, also technical stuff, you see both sides. Total tool life, especially in small batch production, this is a hard one. I dare to say, based on my own experience, that 30% small batch production, especially high stainless steel machining, small batch, 30% of the cutting edges are in the recycle bin, and they still have capacity to cut. So it's a major thing here to try to see the full picture. Process optimization, what are the best cutting conditions, what are the best cutting tools. Value stream mapping can be applied. Some of you perhaps do that on a machining process. See where, the waste is in the process, and how can we avoid it. Standardization, because a very important thing I see also so often that one workplace, 10 operators, and every operator has his own tool for certain applications, and each one has certain argumentation for it. I don't say it's wrong, but is that what we want? 10 different tools for the same application in one workshop. Advanced technology. People say, but HPDC cooling, that's special tool holders, and they are expensive. But again, and I go back to my first point, cost benefit. And advanced technology is going to give you a lot. But part of advanced technology is when you have to purchase it, it's a bit more expensive. Material selection. If you have impact, if you have influence, a machinist can always put on the table, why not to use easy machinable stainless steels for certain workpieces? It would gain a lot of money. It would reduce the costs in machining, of course. Purchasing people will say, but it's more expensive to buy. Education and training, I always come back to that. Make sure with your suppliers, you have, I would say, key partner agreement type of thing. That you can count on certain things. And of course, in the present world, sustainability is something, especially for stainless steels, because we are going to consume more tools, we are going to consume more time, we are going to consume more money, the demands on people is higher, all things that are subcategories under that big word, sustainability. Sustainability in stainless steel machining applications is a bigger challenge than in traditional material applications. Stainless steels, it's a family name. There are different groups, mainly based on the structure. Faster tool wear, more issues with surface quality, higher machining costs, lower productivity is a reality if I take my traditional construction steel as a reference. That means that from a technical perspective, from a technological perspective, selection of cutting tools, selection of cutting strategies or machining strategies, cutting conditions deserves more attention. And by doing that, what we want to influence is the effectiveness and the efficiency of the process. Because, we have to keep under our attention economies. Knowledgeable and skilled people, obviously. Practical geometries is an important thing. You can have situations where you face frequent breakage of cutting edges, not due to the cutting, but due to ship evacuation. So also deserves your attention. Notch wear, build-up edge wear, and plastic deformation are most of the time present on cutting edges. Don't spend too much time trying to make it disappear, because it's impossible. It belongs to the game. Accept it. High feeds, high depths of cut is the terms you have to think on. Cutting speeds are the third factor. There you balance to make sure your cutting temperatures are in the correct zones. Rich emulsion flood cooling is okay as a cooling system. HPDC is better. I haven't seen any situation where HPDC didn't outperform by far typical emulsion flood cooling. There are situations, I'm thinking on rough milling applications, where dry machining is even better. And that is depending on if you can't reach the needed temperatures in the high performance domain, and by selection your offshore cutting conditions, yeah, you have to try to find other ways of artificially kind of increase your temperature in the cutting zone. And one of those things one could do is leave the cooling away. Final thought each time I talk about machining is it's about people. Make sure that's my final thinking here. Make sure your people are trained, educated, have all the needed information if they have to machine stainless steels. Thank you for participating, for watching this presentation. On behalf of my colleagues and myself, I hope you found it interesting. If you have questions, if you want more information, if you have certain things you want to share with us, please do so. We always appreciate that communication is there. And if you have questions, put them in the comments, and we make sure that we handle them as quickly